So hello everyone. So we'll wait for 1 minute and then we'll start. Hello, am I audible?
Yes.
Yes, sir.
Okay.
Yes, sir.
Okay, thank you. So I'll just share the YouTube link. In the chat. And also the document where I'll be uploading the drive link. You'll get the documents here once the tutorial is complete. So yeah, so let us start. Yeah. So today we'll be doing Bayes learning. So till now we have been training functions like this from x to y in case of supervised learning. So we'll be today, but actually what are we trying to do? We are trying to learn some distribution of x and y. So today we'll be seeing how to learn the distribution itself. So using a statistical models. So instead of using function approximators, we'll be using statistical models to learn the distribution of the data. The data using statistical models. So today this is the plan. So we'll be mainly dealing with Bayesian models. So therefore we'll be starting off with what is a Bayesian model or Bayesian statistics. So Bayes was a member of the church, and he had come up with this idea that we update our beliefs we have some priors in ourselves, and we update our beliefs according to what we observe around us. So and later it was mathematically formulated in probability, and therefore we acknowledge his ideas, his philosophical ideas, and therefore we call these type of statistics where we update our beliefs according to the world we observe as a Bayesian statistics. So that was the story behind Bayesian statistics. Let's start. What is Bayes' rule? So I'll give you an intuition. So look at this Venn diagram. So what probability of A given B? What does this mean? This means what is the probability of an event A given B has occurred. So it has been told that B has occurred. Therefore, the region that the event that we'll be observing is in somewhere here. The event E belongs to B, the set B. So therefore, what is the probability that it also occurs in A? So that is nothing but when this will be at the intersection of A and B, right? So if it occurs, if it is in the intersection of A and B, so then given B has occurred, A has also occurred. So A intersection B, and we normalize it by the probability of B. So I'll give you an example and then you'll understand. So think of, there are 10 objects, here there are 12 objects, and in the intersection you have 3 objects. So this is A, this is B. So it is told that what is the probability of A given B? Can anyone volunteer and tell me what is the probability of A given B?
Probability of B given A.
From this Venn diagram, can you just directly tell me what is probability of A given B?
3 by 12.
3 by 15, right? Yeah.
3.
So the total number of elements in B is 15. 12
okay.
plus 3. So I've written this part as 12, this as 3, and this part as 10. So that's, I think you've understood that. Yeah.
0.2.
Yeah. 0.2. Yeah, correct. So this is the idea, basically. Given a set has occurred, what is the probability that other set has also occurred? So so this is the geometric view or the intuitive view of Bayes rule. So that's what I've written down here. So we'll be doing a question on Bayes rule, and then we'll be going through statistical models. So let's see what the question has to offer. So what in a machine learning classifier accurately captures the brain injuries 85% of the times. So let us draw the contingency table here. So this is true and this is prediction. Yeah, any question? If you have a question, you can ask me. So here we are seeing true and predicted, these two values. So this is a true probability. So 85% of the time. So this is the region where your brain injury has occurred. Injury is true and your prediction is also true. So this is 0.85, right? So we'll try and learn how to fill up contingency tables. I've already covered this in the first tutorial. We'll be doing it again. Let's do it. So it gives a true negative at 90%. So 90% of the times it gives a true negative. Is it 90%? Yeah, true negative 90% of the times. So what does a true negative mean? True negative means, so this is positive, this is negative, this is positive prediction, this is negative prediction. So true negative means this entry. So you're making a correct prediction and you're making a negative prediction. So that is 90% of the times you're making this prediction. So you're telling me what is, it is estimated that only, is it type error 1? These are errors that you are making. Say this is a classification model and you're trying to make an say accuracy problem. So you're giving some probability of making an error. So that's you're seeing from the model itself. So is that clear? Yeah. So it's an accuracy type of a model. So you can directly calculate that. So you can see that it makes a correct true positive 85% of the times, true negative 90% of the times. So how many of the data points? So this like 0.85 is this one. So given probability, given an injury, you say true is 0.85, right? If you have a doubt, you can ask me. You say probability of, therefore probability of false given an injury is, can anybody tell me?
Right.
0.15, right?
1.15.
Yeah, so law of total probability. So this is 0.15. So you can see the prediction is negative here. So its prediction is negative given an injury is positive. So this is 0.15 and similarly this is 0.1. So this is probability of saying true given no injury. So I think you have understood up to this. So let's go to the question. What does after we have filled up the contingency table, let's do the rest of the question. It's estimated that the probability of the number of people that take a scan, only 0.1 of them have injury, right? So this is the prior, you say. So this is the knowledge of whether say anybody coming to the scan, what is the probability that you will have an injury? That is only 0.1. So now we want to find probability that a new sample is diagnosed with a brain injury. So you want to find probability of true by model. So how to do this? Any idea? So before I go and explain this one, so you'll have to, so we came to Bayes rule, we'll be using Bayes rule in a different way. So come to this diagram, concentrate on this right on the right hand side of the page. So you can see that you want an event, say probability of A to occur. So how can you write A? You can write A as a sum of probability of A intersection yi, right? I have the way I have drawn this figure. So you take intersection of A with yi, say this is the first intersection, this is the second intersection, this is the third intersection, and you sum these together and you will get the probability of A, right? If given that the condition required is that y for every yi and yj must be exclusive and exhaustive. Means it must sample the entire sample space and there must not be any overlapping. Therefore, then we have to consider all the overlapping cases. So every yi event must be non-exclusive, must be exclusive, not independent. You must not confuse it. Given exclusive, they are always dependent. So one has occurred, you have complete knowledge about the other. So you can, these yi's are different events. So if you take the intersection between yi's and A, so you'll get total A. Is that all right? So from Bayes rule, you can write this as probability of A given yi into probability of yi, right? If you have a doubt, you just ask me now. Otherwise, we'll be going to the question, solve the question.
Can you explain the right side diagram,
Yeah.
that square part?
Yeah, I'll go down and I'll explain. Yeah. So it will become so law of total probability. Say this entire sample space, this is the entire the event space to be exact, can be divided in this form. So this is y1, this is y2,
Okay.
and this is y3, y4, y5 and y6. So and you have an event A, say A. So and you want to find the probability of A. So how will you find? So you have information about, sorry. So you have information about yi's. You have information such that probability of A given y is given to you. This is given. But you have no information about probability of A. Did you get the intuition? So given yi, you have the complete information of what event can happen, what probability can happen, but you don't have the total probability of A, you don't have an information about that. Is that okay?
Okay.
Now next thing, then how can you do that? So you can see that this probability of A can be written as the summation of these areas, this area plus this area plus this area plus this area plus this area, right? So if you get, so what are these areas? These are nothing but summation of A intersection. Okay, so if this was covered in Mr. Pinto's tutorial, so but people are having a doubt, so I would like go to the next part. So probability of A given, you don't need to worry about it. So I'll be doing, this is just the foundation we'll be needing throughout. So I'll just lay the foundation once. So is that okay, Nirmala, now? So
It's fine. I understood.
yeah. So you just need to take the intersections and you'll get all of these events. So here in this question, so what will you do? So you can condition, you want to say this model is predicting true. So you can condition like this, right? Probability of true given an injury into probability of injury plus probability of true given no injury into probability of no injury, right? Is this clear? So you condition. So conditioning is the heart of Bayesian learning. So once you know there's an injury, you know what is the probability that the model will predict it to be true, and then you just multiply. So this, I just use law of total probability. Is that okay? Do anyone have a doubt? Then we'll be going to these. We'll be like solving this question. Otherwise, like do mathematical analytical calculations, and then otherwise we'll be going to the next question. So anyone has a doubt here? So I have conditions, model predicting true given that there is an injury. So this is this case, and model predicting true when there is no injury. So this is this case, right? So if you have a doubt, it seems that no one has a doubt. So probability, so I've just written it down here. Probability of an injury is this. This will be required, and probability of injury given no, this is 0.1. So that's what I've written. Just these numbers, I've just written it down here. So you just do the math, put the values here. This is 0. Probability of yes given injury is 0.85. Probability of an injury is 0.1 plus 0.1, that is probability of yes saying given there is no injury, and probability of no injury, that is 0.9. Is that okay? If anyone has a doubt, you just ask me now. Otherwise, we'll be going to the advanced topics. This is just the warm up for the day. We'll be using this extensively throughout. Is this okay, Nirmala?
That's fine.
Yeah, you
Understood.
Yeah. This question you understood, right? The specific.
Yes.
Yeah. So whenever you have been given some information given in a random variable, so you try to condition and take the law of total probability. That's the heart of Bayesian learning. So this is what I wanted to convey through this first 15 minutes of today's tutorial. So now we'll be using this concept throughout. So let's start off with an example. Yeah. Yeah. Somebody asked a question. Okay. So it's reassuring that everybody is saying it's okay. So let's start. Let's go to the next part. So let's introduce what is Bayesian decision theory classifier. So you have something like this. So I'll give you the intuition of what does this mean. So you have, say you have k classes in a classification problem. Say the imaginary data set, you have cat, dog, mouse, and so on, kite. So you are given a data and you want to classify one of these, say dog. So how will you classify using a Bayesian model? So one thing you can do is you can make functions. So how do you generate functions? You can do something like this. Given x, gi will say the probability of dog. Say dog. Probability of cat will g day will say g's cat will say probability of cat. Once it sees these models. So what we can do is you have this classifier over here. It will take all these values. So from every cat, dog, which I've seen, they are individual some models. They'll be giving you some probability, and it will give you the label corresponding to highest probability. So this will integrate all the individual models, so to say. Is that okay? So is the intuition clear? So you have multiple models giving you probabilities. So given X, it will say what is the probability. The cat model will say what is the probability of being a cat. The dog model will say what is the probability of being a dog, and so on. And say the classifier will input all these numbers 1 to n, cat, dog, and so on, and it will give you, say the maximum probability was given in form of a dog, so you get dog as the output. Is that okay? Of all the probabilities, maybe dog was maximum. So I see no questions. So let's take an example and then it will be clear. So I'll give you an example over here. So again, so let's take gi of x as the class I, probability of class I given data x. So given a data x, what is the probability that your model will output? Yeah, what is the probability that the model will output? Omega I. So using Bayes rule, so what is omega I given x? What can it be written as? Can anyone prompt? According to Bayes rule, so you can
probability
write
of x given omega I.
Yeah.
X
The probability of omega I
into omega I.
Okay, so
probability of x
that is
given
correct.
omega I. Yeah.
Divided by probability I.
Yeah. So this I can again write. I can condition omega I in form of x and multiply px. So this is what we have covered. No. This is what
it is x x given wi.
Yeah, it is x given wi. So I was like, yeah, sorry. So that's why it is not coming up. So I'll go into the same form. So this is what you see. So I have sort of made a mistake. Oh, sorry. So this is correct. So this is omega I given x. So you will condition on x given omega I
into omega I.
Yeah.
Divided by
x. So probability of x is fixed, right? So you need, why did I do this? So I'll tell you why I did this. So generally, say you have a distribution. So given a class wi, so you will have a distribution. This is the intuition that you need to understand. What is the data that is given to you? So this is called the data. So this is called the likelihood and the knowledge that you generally have, or the data likelihood. So what does this mean? So say you have the distribution of, so say x is the feature weight given cat. So that is some distribution like this. So this is what you generally have. So you given a class, you will have a distribution of weights. You are not given what is the distribution of the class given the weights. Is that clear? So you will need to find the opposite one by doing the Bayes rule. So this is what is generally available to you. This is called the likelihood function. This is the data probability, so that's not important. These are the priors, class priors, and this is the posterior that you are interested in. If you have anyone has a doubt, I'll solve that and then we'll go to the next part. Does anyone have a doubt here? I guess it's okay. So you can see.
Can you explain likelihood?
It's a marginal probability, correct? So yeah, P of x is the marginal probability because you're marginalizing over omega. So sorry for the notational problem. So which one you want me to explain?
The likelihood.
Yeah, so you want me to explain what is this, right? Why are we given this data? That's what you're trying to ask, right?
Yes, sir.
Yeah. So because, again, I'll go to that last part. So generally what you're given, say you have a class called cat and you have modeled weight for the cat. and you have a class. This is the weight, say, for the cat, and you have a weight, say, dog. So somebody is unmuted. So dog. So you have another distribution like this. Is that okay? So cats are lower weight. This is some in form of kg, and this is some probability, right? So cats are generally lighter than dogs. That's what I've plotted. So you'll be given this, and you'll be randomly sampled. So you'll be given this point, and you'll be told what is the class that you are going to output. So for that, what will be given is, you'll be given weights, and you'll have to say the class. But you're given the opposite data, that given the class, what is the distribution? Is that clear?
Getting, sir.
Yeah. I think the intuition is clear now. So let's go to solve this question. It's a very simple question that we'll do. So this probability of x, the marginal is summation of probability of x given omega I over all I in the classes.
Given this point,
yeah. So this is your probability of x, right? That is a constant for the data set. So you can just leave out this constant in case of a discriminant function. You don't need to calculate it. That's what I've done. You've just written a proportionality here. So all constants can be dropped. So what is marginal probability? Marginal means you are just for a particular value of x, you're taking the summation over all the classes. That's it. There's nothing more. So that's the distribution of x, to be exact, from where you're sampling x. You don't need to worry about that so much during this learning. Is that okay? That's the distribution of x from where you're sampling. The entire distribution. So that is constant, because that sampling distribution will be fixed throughout. So you don't need to worry about that. So that's fixed. So you'll get this function for every class. So because log is a monotonically increasing function, this is the log x, and this is x. So if this is true, so this is also true. So why are we taking log? You'll be just seeing now. This will help you in solving many questions. So I'll give you an example. So why are you taking log? So for every class, you'll be outputting something like this. For every class, you'll output this number, and the discriminant function will give you the maximum probability. Class corresponding to the maximum probability. Let's see now. So say this feature x is distributed as a normal distribution, bivariate distribution 3, 6, and this is the standard deviation of the covariance matrix. For these are two classes that you have, and the some feature is distributed in this way. Say the weight and cat and dog is distributed in this way. So I think all of you know a 1D Gaussian or a 1D normal distribution. Normal mu sigma square is given, the PDF of this distribution is given by 1 by sigma root 2 pi e to the power exponential of x minus mu by 2 sigma square. This can be extended to multivariate distribution by this. So it's very simple. So you can go through this. So x is of the form mu plus az here. So no need to go through the exact mathematics. So why is this true? But anyways, we'll be dealing with, here you deal with variances, here you will be dealing with covariance matrix. So sigma square is variance, so you have sigma square inverse, and here also you have covariance, so that is inverse. Sigma square is analogous to capital sigma in a multivariate setting. So this is the distribution for a given density. This is the density of a multivariate Gaussian. So we'll directly use this here. So let's calculate the inverse of these matrices. So what is the inverse of sigma 1? Can anyone tell me? So I have purposely given diagonal matrices for easy calculation. So what is the inverse of sigma 1?
Sigma minus 1, no? Or 1 upon sigma.
Yeah, so you don't need, right? So it's a diagonal element. So diagonal is 2 comma half. So if you just multiply the diagonals, so you see sigma 1 inverse sigma 1 is I. So because diagonally, you're just multiplying the diagonal element. Since it's the diagonal matrix, you don't need to even compute all the adjacent matrices and all, covariance, adjacent matrix and all. Is that okay? And determinant, nothing has to be calculated. Adjoint matrix, you don't need to calculate. Because diagonal matrices, you can just multiply. See, 2.5 will be a 1, 2.5 will be 1. Is that okay? So if there is a problem, I'll just show this. 2 half 0 0 half 0 0 2. So you multiply these two matrices. You have 2 times half, that is 1 plus 0. So 1. Next one is 0. So 2 times 0 0 times 2. Then you have 0 times half and half times 2, that is 1. Is that okay? The diagonal matrices, you just take the inverse of the diagonals, then you get the inverse of the matrix. You don't need to calculate anything. So what will be the inverse of the next one?
2 2 2 0 0 2.
That's the that is this, right? Sigma 2.
Half 0 0 half.
Yeah, half 0 0 half. Just take the inverse of the diagonal. That will do. So let's calculate. I'll just do this down here so that there's no clumsiness. Yeah. So we have seen probability of x. This is a vector, is given by 2 to the power of d by 2. This is the determinant half e to the power minus half x minus mu transpose sigma inverse x minus mu. So sigma is diagonal. So what we need to do is, so if you take log of this, so since we are calculating log px of this is what you are doing. So what will it be? So you'll have some constants here. So this is a constant log of minus 2 pi to the power d by 2 minus half log of determinant of the covariance matrix and minus of, so exponential, you just remove the exponential, you get x minus mu transpose sigma inverse x minus mu. Is that okay? So if you take log, what do you get? You get this. So this is the constant, you can drop it. So you can, this is a constant, drop. So this is same for both sides of the problem. So you don't need to keep it. Is that okay? If you have a doubt, ask me now only. Otherwise, we'll go into the calculation. So what is the determinant of 1? Determinant of the first covariance matrix. And what is the determinant of the second covariance matrix? So it's just the diagonal multiplication. Yeah, 1 and 4, right?
1 and 4, sir.
Correct. Very good. So sigma 1 half is 1 and sigma 2 half is 2. That's it. Directly apply this. That's what I've done. See, this is what I found out in the last end of the page, right? Have I written anything different? I haven't, right? So I can go ahead with the calculation, right? Yeah. So somebody is assuring to see somebody saying yes. So I just put value of 1 here in the determinant. It goes to 0. Log of 1 is 0, and you calculate this matrix product. That's it. So you do the math. It's very simple. This is the diagonal matrix. So this will be 2 times x1 minus x3 and half times x2 minus x6. And you multiply x1 minus x3 and x2 minus x6. So that's what I've written here. This is exactly the same thing. Similarly for 2, so we have seen sigma 2 determinant is 2. That's what I've written. That is equal to 1. And since this was equal to 4, so you have half out there, right? Yeah. So this is sigma, so you have half into 2. So this is equal to 1. So this is 1. And similarly, you have sigma inverse is half comma half 0 0, and you have x minus 3, x minus 3, and x plus 2. So you get this. Is this okay? Why I did this? So I just showed the step. I guess it is okay, right? So this is x minus mu, this is sigma inverse, x minus mu 2, sigma inverse, x minus mu 2, right? That's what I've written. Yeah, so I don't think there is any confusion. So you get two numbers here. So now how do you actually get a boundary? So you get two functions. So now is the point where you need to understand. And since I took the priors to be 0 as 0.5 as well, so I'll just show that as well to you just for the sake of completeness. I have assumed the priors to be 0.5. This 0.5 and 0.5, so I can drop these constants as well from the calculation. So now say we have two functions, g1 of x and g2 of x. So this is giving me some probability. This is giving you probability of class 1 given x. This is giving you probability of class 2 given x. Is this okay? Now how do you think that we can generate a single function or the g function? This is nothing but argmax of g1x and g2x, right? Or you can write this as g1 minus g1x minus g2x greater than 0. Then you can classify this as class 1 else class 2. Is this okay? So if this is more, this will be greater than 0. So you then classify as 1 and else you classify as 2. So you can have gx is equal to g1x minus g2x. Correct? And if g of x is greater than 0, omega 1 else omega 2. Any doubt? And where? Yeah, any doubt?
No.
Okay, so you have these classes, say, so you know that if a point belongs to this class, g2 will be outputted. Yeah, you will be exactly, we'll find both the probability of both the classes and forgive the output the probability of the maximum class. That's what I'm doing. G1x and G2x are the probability of each of the classes. Is that okay?
Yes.
Yeah, great. So if you have a point this, so G2 will have more probability, so it will be negative. So how do you say where will the model be confused? When G1x is equal to G2x, right? So this is called the decision boundary. 50-50 chance. So this is somewhere like this. So if you equate G1x equal to G2x, you get the decision boundary. That's what I have done. So Gaussians are generally used. So I've equated G1x and G2x to get the decision boundary. And you can see this is a parabola. Simple algebra calculation can give you this equation. So you can see it's a parabola. So this is a very helpful thing Gaussians can do. Gaussians can model a wide range of parameters. They can model lines, they can model parabolas, ellipses, all conics basically. So any doubt in discriminant functions? So otherwise we'll be going to the next part. That is the maximum likelihood estimation. This is a very interesting thing that I will be doing. Do you have any doubt? So there is no more doubt, it appears. So let's go to naive Bayes model or the maximum likelihood estimation. So if time permits, we'll be also seeing how linear regression is also a maximum likelihood estimation, and we'll also see how we can impose priors on it or bias. In the first class I have said high bias, low bias stuff. Time permits, we'll do that as well. So bear with me. So where do I go with it? So yeah, so I think this can be followed. So you assume that X is sampled from some distribution. Is that okay? So you assume that this is being sampled from some distribution. And you assume the distribution. Step 2 is assume the distribution and fix the distribution. Or the class of distribution. And then estimate the parameters of it. So now the question arises, how do I do it? The question is, how do I do it? So here X has both labels, X and Y. So there is nothing to be confused about. X can be, Y is just a special dimension is X. You can always encompass Y in X. That's not a problem. So this is the total data. So if it is a supervised learning problem, you have X comma Y as each of the X sites. If it's an unsupervised learning, you have only X. So if you have any doubt, you can regarding this notion, you can ask me if there is any, if somebody begs to disagree. Otherwise, we can go to the next part. So yeah, so there is something that we can do to estimate the parameters. So what is that? How can we write? So I should not write given theta. So I should write, because theta is not a random variable. You have fixed the class and theta is the parameter that you want to estimate. So theta, some distribution P of X of theta, or rather D of theta, say Xi is distributed so some distribution D of theta. This is the assumption that I make, where I know the closed form of D. If you have any doubt, you ask me. Otherwise, I'll be going through, again I'll be explaining anyways. So you have something like this. So you have sampled, you don't know the actual distribution, but you want to know it from the data that you have. So you have sampled 1, 2, and you have sampled n points in the distribution, and you have given theta. So what is the assumption I'm making? So you are having this distribution, so you're sampling each of the points independently and identically. So why am I making this assumption? If each of these points are independent, how do I benefit? So this is why it's called the Bayes model, because nothing depends on anything. So if they are independent, each Xi is independent of Xj for I not equal to j. Is that clear? So each of the data point is independently sampled from the distribution. So Xi is sampled from distribution d theta, IID samples. If you have a doubt, you ask me now, because this is the foundation that we'll be using throughout the next 30 minutes or so. Is that okay? Each of the data points is independent. So people who were sort of interacting, is that okay with you all?
In left side, estimate A comma B, what is it actually?
No, don't look at the left side. I'll give, there's a specific examples I'll be giving. Don't look at that. So just look at the right side. So if you tell me to write somewhere else, so don't just think of that. So I'm just telling some x1 and x2 and xn, they are being sampled from some distribution, and each of them are independently sampled. Is that okay? This much is clear, right? And the distribution closed form, the PDF or the density, you know in some way. These are the assumptions I'm taking. So I've written down the assumptions. So assume a probability distribution and data points are IID, assume to be IID from that. And then estimate the parameters. These are the two steps that you need to do. So what is the, so do you have an idea why am I taking this independent assumption? So it's a very good assumption to make, because the data points need not be correlated to one another. Because the data points may be like, you can say it runs by a batsman, another batsman, and so on. So these things, or you can say the smoke levels and the pollution levels in a city. So one city and one city may not be dependent. So it's a good assumption to make. But why am I making this assumption mathematically speaking? If I'm able, I should be able to model everything. So I'm making this independent assumption because, so you remember, right? So A given B is equal to A if A is independent of B, right?
Yes.
So probability of A comma B can be written as probability of A given B into probability of B, that is equal to, you can just productify these equations. Correct?
Yeah.
So that's the reason I'm writing this way. So 1 equal to 1 to n probability of xi given theta. So this is the crucial jump that you're making. If anyone has a doubt here, they can ask, otherwise we'll be going to the specific case of how we are going to estimate these parameters theta. So our task here is to estimate this. So how do you think we can estimate this parameter? So this is called the likelihood function. So this is some function L of theta where probability of xi I equal to 1 to n. Similarly, this is also, you can also take a log likelihood. In that case, you will take a log of this. So since these are all increasing functions, both are equivalent. So in this case, it will be summation of I equal to 1 to n, something that you do in linear regression. Probability of xi, this is called the log likelihood. Just a note, side note. So probability of x is complete data likelihood, so not anything else. So that's a complete data likelihood. So is this clear? So this point is clear, right? So how do you think we can estimate parameters theta? So theta star MLE is given by argmax of theta L of theta. Is that okay? Is this sensible? So you want to select the, so say this is W and this is probability of, this is the parameter, probability of x given W. So the idea is to output this omega. That maximizes the probability of the distribution. Is that clear? I think this pictorial explanation will give you the intuition. So the idea is to find that parameter and maximize the probability of the samples coming from the distribution. Is that clear?
Yes.
Yeah, so that's reassuring. So let's go to this problem. So how do you think we'll estimate? So I have taken a problem where each of the xi are defined from uniform AB distribution, right? So uniform AB has a PDF of, what is the PDF of x? 1 by b minus a, if it is between b and a. So I am taking a to be smaller and b to be larger, 0 otherwise, right? So it's something like this. So it's b by a and this is b, and you have some uniform probability such that this area is 1 and this is all 0, right? So you can understand why this is the PDF. So you know the PDF has to integrate to 1. That much I expect you all know. So integrate of px should be equal to 1. That's why this is 1 by b minus a. So it has equal probability from being sampled anywhere in between. Here, anywhere it can have the same probability. There is no difference. And outside a and b, this is 0 probability. Is the distribution clear? I guess if you have any doubts regarding the uniform distribution, you can ask. Otherwise, I will assume that you all understood what's the distribution I'm talking about. So here, I want to estimate both A and B because they are the parameters of the distribution, right? So how do you estimate them? So I've written this here. So every xi given a comma b is 1 by b minus a, given a is between a and b. So I assume that all the xi's is between, I'll repeat. So let's write it somewhere else. So what is a PDF? The probability of some x being between a and b is given by, this is just, this I should not be doing, you should know this, right? What is the probability? This is the area under the density curve, right? This is clear, right? This is p of x and this is x. So between any a and b, or say write x1 and x2, Is that okay, Khushi? Between x1 and x2 is given by the integral. This integral or this summation in case of a discrete variable. So, yes, thanks. So, in this case, what do you think, if it is a uniform distribution, what should be the height of this? So, since the base is b minus a, the height should be 1 by b minus a, right? So, the area is b minus a into 1 by b minus a, that is equal to 1. You want the total probability to be 1, right? So, the area under the curve must be, under the density curve should be 1. Is that okay, Khushi? So, for a uniform distribution, uniform AB, you have this height as 1 by b minus a. This is A, this is B. Is that okay? That's great. So, that's what we have done here. So, each of these are distributed in this form. So, I can productify this, and so this will be 1 minus b minus a into 1 minus b minus a, and so on n times. So, that's what I've written. So, if all the xi's are between a and b, so then you have this, otherwise you have 0, right? Because otherwise the probability of one of them was, so I'll give you an example. So the data point, so this was say AB, and one data was here. So what is the probability of this data being here? Probability of x given AB, this is 0, right? So you multiply 0 with the product, so that becomes 0. Did you get the intuition? I think there's some doubt. If anyone has a doubt, you ask immediately. Okay, so that's great. So now if it is outside this interval, so you will have a 0 probability for that. So you want A and B to encompass the entire data. So how will you maximize this? So you will only be able to maximize this when this is the smallest, right? B minus A has to be the smallest. You want to make B minus A the smallest. Is that right? So because it is 1 by b minus a, so 1 by b minus a will be largest in case where b minus a is the smallest. Is that okay? Is that argument okay? Is why do you want it to be as small as possible? Because 1 by b minus a, we want it to be as large as possible. Is that okay? I guess that's okay. There's simple maths. Great. So how will you make it as small as possible? By taking the extremes of the data distribution. So you have some distribution like this, some data points like this. So you'll be taking A to be this and B to be this. So any other A and B you see, it's more. So if I choose A2, B2, A1, B1 is more. Therefore we cannot select that. Therefore A has to be minimum of A, A1, A2, A3, A4, AN, and B has to be the maximum of them. Is that okay? I think this gives you an idea of a good idea about what is maximum likelihood estimation. So now we have, yeah, Akshay. You want to, Akshay, you have a question?
No. So we'll enlarge this area such that to which point we'll enlarge it, like maximum
Exactly.
which we can do.
You want to minimize the enlargement. The minimum the enlargement is, the better is your likelihood, right?
Yeah.
So you will take the minimum of x to be your for A point and maximum of x to be your last point. So that's the smallest interval that you can take. Otherwise the probability will become
Okay, got it. Yeah, thank you.
Yeah. So this was like the simplest. How can A minus B minimum if selected is? How can A minus B minimum if A and B area selected is maximum? Area selected is not maximum, right? So you are selecting, if you select any other A and B, what will be the probability or what will be the likelihood? For these it will become 0, right? So that will become 0. So you cannot select anything less that has data points outside A and B. You have to select A and B such that it encompasses each and A and B. That is trivially true. Otherwise it will become 0, trivially. Probability will become 0. And then you will A and B distance, if I maximize, I can take any A and B as large as possible. So that will help me. But in that case, 1 by B minus A will be very small. That I don't want. So I want, if these are x, x1, x2, ... x3, x5. So I want x1 to be A and x3 to be B. So in that case, this A and B will be the smallest. Is that okay? Navnithan? Navanithan? Is that okay? Yeah, great. So last thing that we'll be doing today compulsorily is the Bayes network. So this up to now we have been doing independent assumption, but some cases there may not be independent assumptions. Some variables may be dependent on other variables. For example, so you want to do a task. For that you need to work from early to complete that, because before the end of the day. So the completing the task and doing it early are not independent. So in that case, if we want the complete data likelihood, so how will we do that? So let's write down the complete data likelihood from scratch. So probability of x1, x2, xn. So any idea how can we do this? So we can sort of condition again. So the basic idea of probability is conditioning. So probability of x2 xn given probability of x2 xn into probability of, rather I'll not write this exactly like this, probability of x1 x2 xn, right? So x2 x3. Is that okay? So I'm conditioning on everything and taking the inference on 1. This is also equivalent to writing keeping x1 fixed. So I see you people are comfortable with probability, so that's not a problem, then it's good. So x2 from x3 to xn, and again you do the conditioning on rest of the variables, and this you can continue until and unless you reach the probability of xn, and you have this as probability of xi, probability of xi plus 1 xn I is equal to 1 to n minus 1. Is that okay?
Yes.
Correct. So here, what is the problem? Can you tell me, any one of you? So if I model some distributions like this, so I'll be having to model all these conditional distributions. That may be very, very cumbersome, right? There can be independent assumptions, right? So for example, say, look at this graph. A, B and C. This is called a Bayes network. So I have written this on the top. So anyways, let's go to that place. I'll show you the example of the graph. So take this example of this graph. So here, so let's avoid this equation first. So in this graph, probability of A given B and C is what? It's just probability of A. So the arrow depends means that C depends on A. So A does not depend on C. So A is sort of the parent of all these, both of the nodes. So is that clear? And similarly, B depends on B on A and C will be given by probability of B given A, right? Similarly, probability of C given A comma B, you can't reduce this any further because C depends on both A and B. Is that okay? So given, so we only in Bayes network you compute only the direct neighbors. So you consider that only direct neighbors have conditional dependencies, and given the direct neighbors, the variable may be dependent on B. See, A depends on B, C depends on A. So by transitive property, C also depends on B. But given A, C is independent of B. This is the assumption in a Bayes network. Is that okay? So instead of modeling all the conditional probabilities, we'll be only modeling. So this has to be acyclic graph. So it has to be a directed acyclic graph. If there is a cycle, it will not work because A depends on B, B depends on A. You will not be able to break it up into parents and children. If you have a doubt, ask.
देखने आया एक बार
Yeah.
क्या तो अभी पता है क्या?
Anufal.
पता है क्या हो रहा है ये सब
Okay. So others are okay with it, I guess. So given this, say sort of given C, E is independent of all other random variables. So given C, given C, A, B, D, this is just probability of E given C in this graph. Is that okay? So in this case, you can directly write probability of A, complete probability of A, B, C as probability of A given BC into probability of BC. This is equal to, you can write, since, or rather I will write this way. So probability of C given AB into probability of AB. So this is C given AB has to remain because C depends on both A and B. Then C depends on both A and B, and A and B I can again condition B given A into probability of A. So you see this can be written as product of probability of xi given parents of xi.
So this probability of B given A comma C is equal to probability of B given A. For which graph we have written it? For the upper one, right?
Oh, just one second. Yeah, probability of C given AB for this one. For this DAG. That's for this 3-member graph. This one.
No, the upper green one. Probability of where you write 3 probability A given B is equal to BA, probability of B given A is equal to probability of B comma B given A.
Yeah.
So
it's for the same graph.
So okay.
So you see C's parents are A and B, right?
Yeah.
So you need both information of A and B to get total information about, say, model C, not total information, but model C. For B, there is only one parent, that is A. So given A, it's independent of C.
Oh, okay, now it's fine. Okay.
Yeah.
So
Because
the thing,
C is not pointing back to B.
exactly.
Yeah.
That's why you need to have a DAG assumption here. That's very essential. Otherwise, this parents of I you cannot break up into, because you will have cycles and all. So you will not be able to break it into these things. The cycle must not be there. It should be a DAG, directed acyclic graph. Did you see the point what I mentioned, Ravinder and Akshay?
Yeah, got it.
So I'll do a sort of an easy example to wind up the main discussion today. And if you are interested, you can stay back for 5 minutes. I'll be also giving you the intuition of how linear regression is also a bias variance trade-off with MLE estimates and map estimates. I'll just do that as a side note. That has been done in the course. So I kept that for the last. This example let us do. So we are told to find what is the probability of D. So you can see the probability of D. Yeah. Hello? Okay. The probability of D has to be given by these. You have been given probability of A try A, B, C, and all of these have been given to you. So how do you think you can model probability of D? So see, D has 2 parents, right? So probability of D can be written as probability of, once you know A, B, you know everything about D. Or if you know these probabilities, you can find out the total probability. Let us write it in a more systematic manner. So let us write as D. Let us marginalize D as D, A, B, C, E, and over A, B, C, E. Is this okay? This can be written as probability of D. So I'll just write this somewhere to the right. Sorry for the haphazard dragging. So probability of sum of D, A, B, C, E can be written as, so you get this, right? Why this is probability of D? So you're marginalizing over A, B, C, and E. So you're taking the complete probability. So that's why it's not a problem. So in this case, so you can write the conditional probability of D given A, B, C, E into probability of A, B. Say all the events of A, B, all these events. These are sets, so you have to write all these events. Y equal to 1, 2. These are all events. So you can clearly see that it does not depend on C and E, right? It does not depend on these two. So I can just write I equal to 1 to n probability of D given events of AB into probability of events of AB. So D is independent of C and E. That's why you take it to find D. Exactly. So our idea is to find probability of D. So this is always true in regard of the independence assumption. You don't need to make any independent assumption for this to be true. Okay. But because you're just marginalizing over ABC, you're taking all the events that is possible, and then I'm conditioning over A, B, C, D, E, and you see that C and E are independent, as you rightly point out. Navnithan, if I'm properly pronouncing your name. That's why you're taking, yeah. So you also seem to get it. So we have to consider all A and B events, all possible AB events. So this can be written as probability of D to occur given A comma B into probability of AB plus probability of D, such that these are all binary random variables given binary random variables. So you can clearly see they are given A bar and A, and all these are given to you. So how many combinations will be available to you here? Anyone?
4, I guess.
Correct. So all the events of these A, B variables, the sigma algebra will have to leave that, have to be considered. Is this clear? So what I have done, so there are 4 combinations possible for a binary random variable. So it's a 2 to the power 2. So for each A and B, you have 0 and 1 option. Can we also take A and B alone case? You can take that, right? A and B, but what is the objective that you are told to do? You are not told to find the complete probability of A, B, C, D. You are told to just find probability of D. What is the probability of D to occur? That the D says is true. What is the probability that D to occur means? Probability of D equal to true. You can, otherwise if you are finding like the parents of all, can we all, Khushi, is that okay? Alone A and B case, you cannot directly take. I am trying to show you why this independent assumption is making you leave A and B. So for a directed graph, you can, for this Bayes model, you can take that, because given this, you are conditionally independent. Is that okay, Khushi? Yeah. Okay. Yeah, this is a Boolean feature I pointed out. So this is a Boolean feature. It's a Bernoulli random variable. Otherwise, you will have to take the integral over all the possible ABs. So you'll have to do something like this: B, A equal to A, B equal to Y, probability of A comma equal to X, B equal to Y, the PDF dx dy over xy.
I hope, sir, this integral one will not come in the exam.
No, this will never come. This is anyways, these are simple integrals also, but you don't need to worry about them. You will be doing it anyways in some probability courses.
Yeah, that's right.
Yeah, so this only you will be given with Boolean variables most probably. I don't think you will be getting integrals. Otherwise, you can use the same concept that we have been using. So this is all the 4 cases you have been conditioning, and that's what I've written here. So you can do the math by putting the values and cross-check the results. If you have any doubt, you can ask me now. Otherwise, people who want to leave may leave. I'll just cover the basics of L2 regularization as a maximum likelihood problem. Otherwise, and then we'll be stopping. Otherwise, that is also being covered in the course. So I'm just doing for the sake of completeness. So if anyone has anything to do, so they can leave. Otherwise, and if anyone has a question regarding any of the questions that are discussed in the class today, they can also ask before we do the optional stuff today. So it seems that no one has a question. So I have the notes that I have written down here, so you can go through the notes. So I'll just give you the intuition afresh so that you do not get bogged down by the notes. So how does it? So viewing. Sir, in WT pattern will be in that I think you will have to ask the course TAs, like some TAs are there in the course website who are not taking, who have this recorded lectures, they'll be able to give you the exact logistics. We are to explain the concepts, we do not know what is the questions that will be asked. We are the tutorial people. The questions will be set by the course. There are two course TAs also who are responsible for setting questions. You can ask that in the group. What is the structure of? They'll be answering your question. So somebody is unmuted. If you could just mute. So why? So generally what I want to say is, if I have a noisy data, I have given you this example last day, I want to fit a regression line through it. So what is this data actually? So this is some lines, y equal to wx plus c, this line, or y equal to mx plus c, and some noise has been added to it. So in matrix form you can write y is equal to w transpose x plus c, and some noise has been added. So this is some noise, Gaussian noise. So here normal 0 1 is generally taken. So you have a normal 0 1 noise that is added to it. So this is the classic problem of linear regression. So you have a noisy line that is given to you and you want to recover the actual line. So you can view that it's a noisy line distribution. So one thing you can see is, the probability. So how is x distributed? So we'll make some assumptions. So y equal to w transpose x plus epsilon. If epsilon is distributed as normal 0 1, what is the distribution of y? This is normal w transpose x plus sigma. So this is, instead of taking 1, so let's take sigma square as a normal variance, sigma square. So I'll show you why. So you take expectation on both sides. So it's expectation on, say, for each data point. So given xi comma w is distributed like this. So yi is w transpose xi plus expected value of epsilon. So I'm just taking expectation on both sides to find the expectation of y. So expectation of y is, this is just the expectation of w transpose xi. Since this is a single point, so that is nothing but w transpose xi. So single point's expectation is just the point, and epsilon's expectation is 0. That is already given. The normal distribution as a mean of 0 and standard deviation of sigma square. So this is your w transpose xi is the mean of y. Similarly, the variance of y is y minus yi bar square. Y bar is w transpose x, and y you have here. So you can directly see, so y is w transpose x plus epsilon and y bar is w transpose x. And you take expected value of this, so you get expected value of sigma square. What is this? This is nothing but expected value of sigma minus 0 square, and that is nothing but sigma square, the variance of the map. So I have proved that y is distributed as this way. If you have a doubt, you can ask me, or I will show you the map estimate now, or the MLE estimate. So it looks like you don't have a doubt. So you can say that, so probability of yi given x, given parameters w, how can we write this? Say the log likelihood I want to write. So that is nothing but log of pi of probability of, so this is not x complete data, yi given xi comma w for I equal to 1 to n. If you have a doubt, you ask me now. This is the MLE thing that we have done. So you recap, right? This is the MLE, maximum likelihood. This is the log likelihood function. So this is log of probability of yi given xi given w. I hope you see this, right? Do you have any doubt regarding this step? Because we have already done this step. So what is this distribution? This is normal 0, 1. So that is equal to 1 by sigma root 2 pi e to the power minus xi minus mu square, or rather y minus w transpose x by sigma square, right? Because it is distributed by normal w transpose x, w transpose xi sigma square. If you have a doubt, you ask me, because this is the beauty of MLEs, because you can model any function approximation using MLE only. Actually, when you're doing some function approximation, mostly you are actually learning the parameters itself. You're doing some MLE only. This is the view I want to give you. So if anyone has a doubt, you can ask. So you can just take the log of this now, and you can drop constants. So you'll see that this is nothing but equal to minus 1 by sigma square yi minus w transpose xi. So what is this? So w you will get as w star is arg min summation of I equal to 1 to n 1 by 2 sigma square, or you can, these are constants, you can drop them. Sorry for that. W transpose xi square. So what is this function? We have already done it in the second tutorial. This is nothing but linear regression, right? I think you got, are you people okay with it? Why is this the linear regression? Just taking the log likelihood, and this turns out to be the linear regression. In map, what happens is, you are given some priors on W. Priors in map, maximum a priori estimation. Priors on W are given. So yeah, so can you tell me what are these priors for? So this will give you the feel good factor for today's lesson, because this will connect lecture 0, tutorial 1, and also this tutorial. All of these will be connected through this thing. So once you're giving priors, this is equivalent to regularization, and this is also equivalent to writing biasing your model. So let us take an example. Say wi's are priors are, say 0. Say you have this some lambda times I. So wi's is, they are given by this prior. So the probability of wi is given by 1 by 2 pi to the power d by 2. Can you tell me what is this determinant of this covariance matrix? This is equal to lambda to the power d, right? D dimensions are present. So e to the power of minus x minus mu, or rather I'm taking 0. So w minus 0 transpose 1 by sigma I w minus 0. W minus 0. So this is turning out to be 1 by lambda w square 1 by some constants. Are you getting this now? Now if you do something like this, probability of w, you want to estimate w, this is the posterior. Once you have seen the data and you have some knowledge of priors, so this given x comma y, you can approximate it as probability of yi given xi given w, probability of w. So this is nothing but, so this you can take outside, and this again you will have log of summation of log of yi given xi w I equal to 1 to n plus log of pw. So you will get this as 1 by summation 2 sigma square summation of I equal to 1 to n y minus w transpose x square. This is same as before, same as MLE. And if you take log of this one, you get 1 by lambda this. So this is nothing but equal to w star will be arg min I equal to 1 to n yi minus w transpose xi plus. So these are all written fairly in my notes. You can go through that. I did not want to make them cumbersome, so I wrote it somewhere outside. So this is some alpha. So you can write. This is the hyperparameter. So this is plus. Since this is taking arg min of this. So you clearly see that if you impose priors, so impose some priors like these. So you had imposed these priors. So you are compelling your model to be near normal 0 this. So you are making wi's to be small. So you want to make them independent and small. This is the idea of constraining it to normal 0 1. Because normal 0 1 standard deviation will fall very fast. And if you take a larger omega, then a larger lambda, it will take a very, very large sort of a bias. So it will bias heavily towards this. So this alpha will be very, very high, and this is very, very, if alpha is very low, then you are free. You are sort of giving a low bias. Low alpha meaning high lambda. So low lambda means high alpha, so gives a high bias. So high bias will take you towards that only. So this is sort of learning with bias. So this is also called regularization. So this is some prior. So to be exact, P of W, this is your probability of x given W, and you reconcile with both and try to learn W given x, something here. Is that okay? So I think this was, if you have a doubt in this part, because this is the beauty of sort of integrating whatever we have done till now. So because from the next time we'll be sort of shifting gears to SVMs and neural networks, so we'll not be able to come back to these. So this is sort of, I gave a overview summary of the mid-sem, sort of a mid-term summary. So it's all the 4 lessons, half of the course is in these 2 examples. So if you have any doubt, you ask me, otherwise we'll end the meeting for today. Anyone? If anyone was able to appreciate this view. So what is it? The drive link is not opening. What is it asking? So I've shared the so it's sort of opening. So let me just copy this. Sorry for that. Even if it is not wait, I'll be anyways updating the drive link to the video on YouTube. You can, if it is not opening, you can see. It's opening, right? I just copied it and opened in incognito. It's opening. Is anyone else facing this issue? I tried to open it just now, it opened. YouTube link. Yeah, I'll just share it again. Oh, this is the YouTube link that I have. So here I'll be anyways, if it is not opening, you can just comment or something. I'll just wait just a second. I'll just share this link again. Or let me share it. Wait just 1 second. So anyone with a link can view it. So is this opening now? So if it's opening, we can stop for today. Anyways, I'll be updating this to the YouTube link so you can view the lectures and the tutorials again and again to get an understanding of Bayesian models. And you can also, yeah, so it's opening, so it's not no more, there's no more problem. So I'll upload these annotated slides on the drive so you can view them. So you have all the drive links there, so you have codes of the last 4 lessons also, and all the annotated PDFs of the last 4 lessons. So if no one has any more questions, so we'll be stopping for today. So thank you. Bye.
Thank you.